In the previous video, we gave a mathematical definition of gradient descent. Let's delve deeper and in this video get better intuition about what the algorithm is doing and why the steps of the gradient descent algorithm might make sense. Here's the gradient descent algorithm that we saw last time. And just to remind you, this parameter or this term alpha is called the learning rate, and it controls how big a step we take when updating my parameter theta j. And this second term here is the derivative term. And what I want to do in this video is give you better intuition about what each of these two terms is doing and why, when put together, this entire update makes sense. In order to convey these intuitions, what I want to do is use a slightly simpler example where we want to minimize a function of just one parameter. So we have, say we have a cost function j of just one parameter, theta 1, like we did a few videos back, where theta 1 is a real number. Okay, so just again, so we can have 1D plots, which are a little bit simpler to look at. And let's try to understand what gradient descent will do on this function. So let's say here's my function j of theta 1. And so that's my, and where theta 1 is a real number. Right? Now, let's say I've initialized gradient descent with theta 1 at this location. So imagine that we start off at that point on my function. What gradient descent will do is it will update theta 1, gets updated as theta 1 minus alpha times dd theta 1 j of theta 1, right? And as an aside, this derivative term, right? If you're wondering why I changed the notation from these partial derivative symbols, if you don't know what the difference is between these partial derivative symbols and the dd theta, don't worry about it. Technically, in mathematics, we call this a partial derivative, we call this a derivative, depending on the number of parameters in the function j. But that's a mathematical technicality. So, for the purpose of this lecture, think of these partial symbols and dd theta 1 as exactly the same thing, and don't worry about whether there are any differences. I'm going to try to use the mathematically precise notation, but for our purposes, these two notations are really the same thing. But so let's see what this equation will do. So we're going to compute this derivative. I'm not sure if you've seen derivatives in calculus before, but what the derivative at this point does is basically saying, let's take the tangent to that point, like that straight line, that red line is just touching this function, and let's look at the slope of this red line. That's what the derivative is. It says, what's the slope of a line that is just tangent to the function? Okay, and the slope of a line, of course, is just, right, this height divided by this horizontal thing. Now, this line has a positive slope, so it has a positive derivative, and so my update to theta is going to be theta 1 gets updated as theta 1 minus alpha times some positive number. Okay, and alpha, the learning rate, is always a positive number. And so I'm going to take theta 1 gets updated as theta 1 minus something. So I'm going to end up moving theta 1 to the left. I'm going to decrease theta 1. And we can see this is the right thing to do because I actually want to head in this direction, to get me closer to the minimum over there. So gradient descent so far seems to be doing the right thing. Let's look at another example. So let's take my same function j. Let's try to draw the same function j of theta 1. And now let's say I had instead initialized my parameter over there on the left. So theta 1 is here. I'm going to at that point on the surface. Now my derivative term dd theta 1 j of theta 1, when evaluated at this point, I'm going to look at the slope of that line. So this derivative term is the slope of this line. But this line is slanting down, so this line has negative slope. Right? Or alternatively, I say that this function has negative derivative, just means negative slope at that point. So this is less than or equal to 0. So when I update theta, I'm going to have theta gets updated as theta minus alpha times a negative number. And so I have theta 1 minus a negative number, which means I'm actually going to increase theta, right? Because this is minus of a negative number. It means I'm adding something to theta. And what that means is that I'm going to end up increasing theta. And so I'm going to start here and increase theta, which again seems like the thing I wanted to do to try to get me closer to the minimum. So this hopefully explains the intuition behind what the derivative term is doing. Let's next take a look at the learning rate term alpha and try to figure out what that's doing. So here's my gradient descent update rule, right? It's this equation. And let's look at what could happen if alpha is either too small or if alpha is too large. So in this first example, what happens if alpha is too small? So here's my function j of theta. Let's say I start here. If alpha is too small, then what I'm going to do is going to multiply my update by some small number. So I end up taking, it's like a baby step like that. Okay? So that's one step you're going to take. Then from this new point, I'm going to take another step, but if alpha is too small, I'm going to take another little baby step. And so if, if my learning rate is too small, I'm going to end up, taking these tiny, tiny baby steps to try to get to the minimum. And I'm going to need a lot of steps to get to the minimum. And so if alpha is too small, gradient descent can be slow because it's going to take these tiny, tiny baby steps, and so it's going to need a lot of steps before it gets anywhere close to the global minimum. Now, how about if alpha is too large? So here's my function j of theta. Turns out, if alpha is too large, then gradient descent can overshoot the minimum and may even fail to converge or even diverge. So here's what I mean. Let's say I start off theta there. It's actually pretty close to minimum. So the derivative points to the right, but if alpha is too big, I'm going to take a huge step. Maybe I'll take a huge step like that. Right? So I end up taking a huge step. And now my cost function has actually gotten worse, because it starts off with this value, but now my value has actually gotten worse. Now my derivative points to the left. It says I should decrease theta. But if my learning rate is too big, I may take a huge step going from here all the way out there. So I end up going out there, right? And if my learning rate is too big, I can take another huge step on the next iteration and kind of overshoot and so on until you notice I'm actually getting further and further away from the minimum. And so if alpha is too large, it can fail to converge or even diverge. Now, I have another question for you. So this is a tricky one, and when I was first learning this stuff, it actually took me a long time to figure this out. What if your parameter theta 1 is already at the local minimum? What do you think one step of gradient descent will do? So let's suppose you initialize theta 1 at the local minimum. So suppose this is your initial value of theta 1 over here, and is already at a local optimum, at a local minimum. It turns out at the local optimum, your derivative will be equal to 0. So let's look at that slope, right? It's that tangent point. So the slope of this line will be equal to 0, and thus this derivative term is equal to 0. And so in your gradient descent update, you have theta 1 gets updated as theta 1 minus alpha times 0. And so what this means is that if you're already at the local optimum, it leaves theta 1 unchanged, because gets updates theta 1 equals theta 1. So if your parameter is already at the local minimum, one step of gradient descent does absolutely nothing. It doesn't change the parameter, which is what you want, because it keeps your solution at the local optimum. This also explains why gradient descent can converge to local minimum even with the learning rate alpha fixed. Here's what I mean by that. Let's look at an example. So here's a cost function j of theta that maybe I want to minimize. And let's say I initialize my algorithm, my gradient descent algorithm, out there at that magenta point. If I take one step of gradient descent, maybe it'll take me to that point, because my derivative is pretty steep out there, right? Now I'm at this green point, and if I take another step of gradient descent, you notice that my derivative, meaning the slope, is less steep at the green point than compared to at the magenta point out there, right? Because as I approach the minimum, my derivative gets closer and closer to 0 as I approach the minimum. So after one step of gradient descent, my new derivative is a little bit smaller. So when I take another step of gradient descent, I will naturally take a somewhat smaller step from this green point than I did from the magenta point. Now I'm at a new point, the red point, and then now even closer to the global minimum. So the derivative here will be even smaller than it was at the green point. So when I take another step of gradient descent, now my derivative term is even smaller, and so the magnitude of the update to theta 1 is even smaller. So take a small step like so. And as gradient descent runs, you will automatically take smaller and smaller steps until eventually you're taking very small steps, and you finally converge to the local minimum. So just to recap, in gradient descent, as we approach a local minimum, gradient descent will automatically take smaller steps. And that's because as we approach the local minimum, by definition, the local minimum is when this derivative is equal to 0. So as we approach the local minimum, this derivative term will automatically get smaller, and so gradient descent will automatically take smaller steps. So this is what gradient descent looks like, and there's so actually no need to decrease alpha over time. So that's the gradient descent algorithm, and you can use it to try to minimize any cost function j, not the cost function j that we defined for linear regression. In the next video, we're going to take the function j and set that back to be exactly linear regression's cost function, the squared cost function that we came up with earlier, and taking gradient descent and the squared cost function and putting them together, that will give us our first learning algorithm. That will give us our linear regression algorithm.